This video is the first video in our unit on energy, and it covers some of the basics about energy through to how to calculate specific heat. So energy, and by the way, I typically during this year in chemistry, you have not had to take many notes because we've had a lot of formulas and calculations and whatnot. And I wanted to be sure that you could focus on writing things correctly. But this unit has a lot of conceptual things that I do require you to take notes on things. So just a reminder, if it's in blue, that means it needs to be written into your notes if you don't already have it on a slide. All right, so what is energy? As you see, energy is the capacity to do work. That makes sense, doesn't it? But we know that there's all sorts of different types of energy, right? So in general, we've all heard of kinetic energy, and we think of that as the energy in motion. The other major category of energy is potential energy. And that might be energy that's due to the position of something. So for example, if I have a book on the edge of my table here, it has potential energy because it can potentially fall off the table and move. So there's that. Or energy of composition. And the energy of composition can be a couple things. It can be physical composition with things like elasticity and whatnot, but it can also be chemical energy. So what you need to know is that there are two major classifications of energy, kinetic and potential, and chemistry figures in both of them. So we aren't so much in pure motion. That's more of a physics thing, isn't it? But we're very much into thermal energy. So we're going to talk about thermal energy in just a second, but know that it is a subset within kinetic energy. And then, of course, chemistry has a lot to do with chemical energy, and that's a type of potential energy. All right, next. How on earth can thermal energy get classified as kinetic energy? Well, if you think about it, if I had a big old iron bar sitting out and it was pretty hot, um, it's a solid, right? And is it moving? No, it's not moving. It's just sitting there, but it is hot. Well, the movement that is in a substance can go all the way down to the atomic level. So we know that as long as the temperature isn't absolute zero, remember that, 0 Kelvin? As long as it's not, then whatever those atoms are that are within that substance, they have some degree of energy in them, and therefore they also have some degree of movement. If you remember gas molecules and atoms just zing around like crazy, right? They have a tremendous amount of energy, and gas occurs when a substance is heated up, right, to the gaseous state. You go down to liquids, and yeah, they're still moving around, but they're somewhat more controlled in how they move, right? And they just slide and slip past each other. And then with a solid doesn't look as if it is moving at all. And yet, when you get down to the atomic level, those atoms are vibrating in place. Okay? So, does all matter have to be moving? Yes, at the atomic level it does, or it's 0 Kelvin, which I'm not aware is even something that has occurred in deep space. What happens to matter as it heats? It gains energy, right? Cooling matter causes it to lose energy. And notice we're talking about gaining and losing, in essence, heat, which is thermal energy. But so heat is an actual thing, and it is transferred between objects, as we'll see in a minute. Cooling is simply the lack of heat, okay? So in all this, you may be wondering, why are we always talking about heating up and not cooling? Well, it's because cooling is simply the absence of heat. All right, that leads us to the first law of thermodynamics. And what is that? Well, it's also called the conservation of energy. Doesn't this sound a little bit familiar? Remember when we talked about mass? We said mass can neither be created nor destroyed, right? And that was why we always had the same number of atoms of a substance on one side of our equation as the reactants as we did on the other side of our equation with the products. The same thing is true with energy. Energy cannot be created or destroyed, but, oh, I hope you can read this. Let me read it to you. But it can be converted into another type of energy, right? So the potential energy that is within something, if a reaction occurs, it can release that energy and it can become thermal energy, right? In other words, if there's a burning process that goes on. Additionally, not only can it be converted to another type of energy, energy can be transferred from one object to another. And you've seen that if you've ever played pool, right? You hit the ball, the first ball with your cue, and if that ball hits another ball dead on, then that first ball completely stops, and the second ball continues at almost exactly the same speed as the first was going. So just as kinetic energy can transfer from one object to another, so too can, excuse me, I'm sorry, I got a cold. So too can uh, thermal energy get translated from one object to another. So what are we talking about when we talk about that? Well, heat transfer, right? So here's your sentence you need to know. Thermal energy, in other words, heat, can be transferred from one object or system to another. Okay? So it does not need to change into a different type of energy, but the heat will simply flow. Just like water will flow to the lowest spot it can get to because of gravity, so too will heat flow until the heat is almost said neutralized, but that's not the right word. The heat is evenly dispersed across whatever it can get to. So if you think about it, on a cold day, what do? You put your hands in your pocket, right? Your hands lack heat. Your coat of the pocket of your coat is warm, so you can just stick your hand right in there, and eventually your hand will warm up. Okay. And there you go. You can take a cake out of the oven. It could cool down. Now, when you do that, you take the cake out. You have on an oven mitt, I hope, and you take it out and you put it down, say, on top of your stove, right? When we talked about a system up here, what we're really talking about is it's not necessarily going to go to one and only one object, but like with your cake coming out of the oven, some of the heat from that cake and cake pan is going to radiate out into the atmosphere, right? Into the air surrounding your cake. You could feel the heat if you put your hand up right over it, right? And then additionally, some of it, if you lay it on top of your stove, is going to get transferred to the top of your stovetop, right? So that's an example of a system that we say the heat is moving in the system to get to another location. All right, let's go on and talk about how we measure temperature. This is stuff you already know. So we can talk about Celsius or Kelvin. Remember that 1 degree's worth of Celsius is the same amount as 1 degree of Kelvin, right? Fahrenheit, we're forgetting about it. We're never going to use it. All right, you must remember what you have learned already in gas laws, and that is 1 degree in K is equal to 1 degree in C, like I just said. 0 degrees Celsius equals 273 K, and 0 degrees K is this absolute zero. And that's the point at which there is no thermal energy whatsoever in whatever the substance is that reaches that temperature. And that is where all things stop. It's more of a theoretical concept than it is in reality, to the best of my knowledge here, as of this year. All right, here's the next thing you need to write down. Different types of matter, when they have the same mass, and remember when we talk about mass, we're going to be talking about grams typically, right? And they're at the same temperature, contain the same amount of energy. Okay, so it doesn't matter, no pun intended, what the object is or what the system is. If it has the same mass and it's at the same temperature, it's got the same amount of energy. All right, so what are we talking about here? What's an example? Well, look at these here. Assume that I've got 10 grams of each of these substances. And as you look at this, I apologize, you may not be able to make out the subscripts. So we're saying iron as a solid at 25 degrees, water as a liquid at 30 degrees, helium as a gas at 20 degrees, and calcium carbonate at 27 degrees as a solid. So which of these has the most amount of energy? Well, interestingly enough, we can ignore all these states of matter here, gas, liquid, solid, solid. We can ignore all that. All we need to do is know that at the same temperature, if it's the same mass, it's got the same amount of energy. And so when we look at this, we can say the one that has the most energy is at 30 degrees, and that's water as a liquid. Okay, which has the least amount of energy? It would be helium as a gas at 20 degrees. Okay, that may be counterintuitive if you think about it, because we think about gases as being heated up more. But remember that the point at which a particular substance becomes, a liquid or a gas varies wildly among all the substances. Next thing you need to know is as we go through this unit, we're going to be doing a lot of calculations, and they're not hard math at all, but you really have to be careful as you do them. And you can come up with some wildly inappropriate numbers. So let's talk a little bit about what those might be. The question is, are these temperatures possible on Earth? All right? Negative 250 degrees Celsius, is that possible? Yes, it is possible. It's extremely cold. It's awfully close to absolute zero, but it's not there, so it is possible. Negative 5 degrees K, is that possible? No, it is not possible because Kelvin can never be negative, right? 0 degrees Kelvin is absolute zero. There is nothing below that that can be measured. All right, next one, 10,000 degrees Celsius. Is that possible? Well, hopefully not on Earth, although it may have been created inside a nuclear reactor or something. That's about the surface of the temperature of the surface of the sun. So that's awfully hot, but it is possible. Negative 275 degrees Celsius. Is that possible? The answer is no, it is not. Because if you remember, absolute zero is negative 273 degrees Celsius. So can't go beyond absolute zero. All right. Next thing that we need to know is, how do we measure this? Okay. So when we measure the amount of heat something has, we use a symbol called Q. It's a capital Q always. It's weird that we use Q, but we do. There was a character in James Bond named Q. He was the guy who made all the really amazing little gizmo that James Bond uses. It's probably before your time, but there it is. But know that we use Q to represent thermal energy, which is the same thing as heat capacity, which is the same thing as enthalpy. Okay? So in other words, it's the amount of heat that that object, whatever it is, or system, currently has. All right? So all three of these words are interchangeable, and you could see any of them on any discussion or test or slide as we go forward. Okay? Next, okay, we talk about Q. When we talk about Q, what sort of units are we measuring in? The main measurement that people use in chemistry is the joule with a capital J. That is used in physics as well. So if you have 1,000 joules, you would either say 1 kJ for kilojoule, or you would have a capital 1,000 and then a capital J, right? All right, so that's the common way that we use it in science and technology at this point. The old-fashioned ways that we use it, of which there will be plenty as we work through this unit, is we talk about in calories, all right? And calories can be a little confusing because when we use the word calories, it, it means two different things. A calorie, when it has a capital C, is actually a kilocalorie. In other words, 1,000 small c calories. Okay? And a calorie, small c calorie, is the amount of energy it takes to raise 1 gram of water by 1 degree centigrade. All right? So you're going to have to memorize all this that's here in blue. Well, actually, everything in blue on this whole page you need to memorize. And we will be doing conversions between big C calories, little c calories, and joules. So be sure that you understand this. So a joule is a very small amount. A calorie is the largest of the amounts. But just think of it. You're probably eating at least 2,000 calories a day at your age. And that's with a capital C calorie or dietary calorie. All right, next thing we need to cover is what do we call phase changes for thermal energy? Okay, we all know that as things warm up, a substance can go from a solid to a liquid to a gas, right? And as things cool down, it can go from gas to liquid to a solid. But the other thing that you need to know, and I hope this is clear on the page, is the name of what things are as they change. So when solid goes to liquid, it melts. So there is a point that's called the melting point. Liquid to gas has a boiling point. Gas to liquid has a condensation point. So notice I'm going forward here, getting warmer, cooling down here, and I have a condensation point to get to a liquid, and then of course a freezing point to go to a solid. You do have a word down here at the bottom that you will need to know, and that is certain solids can, in the right conditions, go directly to gas, and that's called sublimation. All right, an example of sublimation is mothballs. So you put a mothball in your closet to protect your woolen clothes so the moths won't eat them. And it's a nice little pellet that's maybe about a centimeter and a half in circumference. When you put it in, you check back a couple months later and it's down considerably to half the size. And you check back a couple months later and it's completely gone. It's sublimated. So it went from being a solid directly to being a gas. Sometimes we see sublimation occur like on a day with a great deal of solar intensity, but when there's ice and the ice is melting. That's Fergus doing a photobomb. Thank you, Fergie. All right. So that's sublimation. Now let's go on. All right. So this graph you'll need to put in your handout. And basically what you're going to do is draw a graph, and on the x-axis here, you're going to say time with heat continually applied. That's very small on my page, but know that it says time with heat continually applied. And then over here you have the temperature. All right, and that means the temperature of the object in question that is having the heat continually applied to it. And when you start off applying heat, let's say that your substance is first a solid. All right, you're applying heat, applying heat, applying heat, and at some point your solid is going to start to melt. And so we're going to call this B on the graph the melting point. And we know that we reach the melting point when we're going this way, right? From solid to a liquid. Now, here's what is absolutely evil. You notice I've got my chemistry is evil here. And that is, as you continuously apply heat here, that solid continues to melt, but the overall temperature of it does not rise. It simply melts, all right? And it will do that until it's completely melted. Once it has completely melted, here at point C, then it'll be a liquid. It'll all be liquid, right? And now the liquid will rise in temperature as heat is continually applied. So I'm going to write liquid right here. Then at some point, right here, D on my little graph, I've got another plateau. And you guessed it, right now is when my evaporation point, evaporation point or boiling point, you can call it either, occurs, right? And we've got the same phenomena going on. It'll continually apply heat, but the heat is just going to change that liquid to gas while the overall temperature of that substance does not go up until it is completely gaseous. So at this point, I've got a gas that has taken place. Now, if I took this gas and I started cooling it down, then at some point it would begin to turn into liquid. And the point at which that happens is called the condensation point. All right? And again, the same thing happens. It just plateaus and will not get colder until it's completely liquid. Then I can continue to remove heat from it. I get down to where it's now going to start to become solid, and I'm going to call this my freezing point, aren't I? Right. So my freezing point and my condensation point are starting at one end of the plateau as I cool, and my evaporation point and my melting point are starting at one end of the plateau as we warm things up. All right? Okay. All right. Next. Now, gosh, I'm going to try to make this a little clearer. I've had a horrible time with that. Does that help? Oh, okay. All right. So now we look at this and we say every type of substance has its own specific heat. But what are we talking about when we say that? So the specific heat, first of all, our chemistry definition is the amount of energy it takes to heat 1 gram of that particular substance by 1 degree Celsius. Okay? So it's the amount of energy, which remember, energy I can express in joules, little c calories, or big C calories, right? And I'm going to have it be per gram and degree centigrade. Calories per gram, degree centigrade. Calories per gram per degree centigrade. That's the unit we're going to use when we talk about specific heat. All right? So here are some examples of specific heat that you can see. And if you look here, you notice Ag, that's silver, iron, aluminum. And what you notice when you look at this is that all three of these are metals, and yet they vary widely in their specific heat tolerances, don't they? So iron is almost twice that of silver, and aluminum is almost twice that of iron. So just because something is a metal or a particular class of material doesn't necessarily mean it's got a specific heat near to the other things that you may also think it should, right? Like metal and metal, or oils and oils, for example. You may be familiar with in cooking. There are some oils you use in one situation and some in another, and it's because of the specific heat of those oils typically. All right, so here's my challenge question. Should we be working in Kelvin and not Celsius? After all, we know Kelvin is a standard for everything. And the answer is, when we're talking about these sort of things, amounts of heat, we're just talking about very specific values. We had to be in kelvins in the gas law because we were talking about proportions, right? And therefore our proportions had to be relative to absolute zero. And that's why we were continually in Kelvin as we worked. Whereas now, all we need to know is the amount between a value or a value is specified here. We're not needing to know anything proportionally as we go forward. So we're always pretty much going to be in Celsius. And we all hate Fahrenheit, don't we? Yeah, so we're done with that. All right, so how does specific heat work? Well, what it does, oh my gosh, do I have this much more? Oh no, I've already done that, right? Oh, okay. Yeah, so here. So specific heat. If it's a small specific heat, that means that substance heats up quickly, but it also loses heat quickly. Large specific heat heats up slowly, but it also loses heat slowly. Now, look at this for a second. We've got ice, water, and steam. And if I didn't have water listed here for its specific heat, and you had to guess what the specific heat of water was, you would probably guess it was 2.0, wouldn't you? Right? That would be the most logical thing. And yet, look at water. There it is at 4.18. That is amazing. It's one of the most amazing things on our planet. And because of this, we have such a better life here on Earth. So, like, it keeps our waters from freezing quickly. They sort of are self-insulating so that it takes a while for ice to form, say, on a river or a lake, and the things beneath it can stay alive because it's not freezing solid down to the very bottom, right? And then it also helps us to keep water from evaporating up into steam more quickly. So this means that more water can be on the earth as water as compared to ice or steam. Um, because of this large specific heat. All right, next, let's go on and let's go to how we calculate things. So remember Q, we said Q is thermal energy, right? Right? Okay. And then we've got mass, and this makes sense that the thermal energy that an object contains is figured out by the mass of the object, the specific heat of the particular substance that object is made out of, and then whatever a change in temperature is that has occurred. So if I wanted to say, how much thermal energy do I need to apply to this thing made out of this substance um, to raise its temperature by a certain amount, I can figure all that out by using this formula. All right. So, and remember, when I do that, I can work in joules, or I can work in big C calories or little C calories as we go. All right. So let's look at the question down here. How much heat will be absorbed by 320 grams of water when its temperature is raised by 35 degrees Celsius? The way I would figure this out is I go how much heat, so that's my Q, so I'm looking for Q. When I know I'm looking for Q, I know that I can be in, let's do calories, okay, with a little c, okay, because I know 1 calorie equals 1 gram times 1 degree Celsius, all right? So that's what a calorie is. So I know that my value is going to be calories, all right? Now, the next thing I say is I start off with 320 grams, and it's water, right? And I know the specific heat of water. So I'm going to have, there's my mass. My specific heat is going to be 1 calorie per gram per degree centigrade. All right? So looks like it says 1 eel, but it's 1 cal. All right. And then 35 degrees centigrade. Okay. And when I come up with that, I will see that my degrees centigrade is going to cancel out, right? My grams are going to cancel out. And now I'm left with 320 times 35. and that will be the number of calories involved in that. All right, let's do another one. All right, let's see. This one, 5 grams of copper is heated from 25 to 45 degrees. It absorbs 37.8. What is the specific heat of copper? So specific heat, remember specific heat is my C. So that's what I'm looking for. So all I need to do is take my formula, right? Right? And if I want to isolate C, I'm going to divide both sides by MT, right? And when I, M delta T, sorry. And when I do that, I'm left with C alone on this side in the numerator, and then Q over M delta T. So let's see, M is mass. So that's 5 grams of copper, all right? Now, delta T, 25 to 45. So that's 20 degrees Celsius, right? All right. Now, 38.7 joules. Okay, so now we're going to be working in joules. So my answer, I'm looking for specific heat, and I'm in joules. So my answer is going to be joules per gram degree centigrade. All right. And this is just 38.7 over 5 times 20, which is 100, right? So it's going to be 3.87 joules per grams degree centigrade. Okay. Let's do another one. All right, let's do that. 435 joules of heat in order to increase. This is specific heat of olive oil. All right, so here we go. It's the same setup, isn't it? Right. So we know that we're going to have Q equals M times delta T. All right. Q is going to be that 435 joules, right? M is 3.4 grams. Delta T, 21 to 85. 85 minus 21 is 64. Okay, so there's my setup. I know that when I get my answer, what I'm going to have for my label is joules per gram degree centigrade. All right, and all I have to do now is a simple matter of math. So that's the end.